We'll be speaking on something involving the words finite, Ramsey, and choice.
Yeah, okay. Yeah, so, well, this is, I'm going to write all the definitions. First, I should say this is joint work. So this is a little project that I carried over the summer with some undergraduate students. And it involves, well, it involves ZF without choice and without even assuming things like dependent choice or anything of the sort. It's basically just bare ZF, many things that you would normally be able to prove you're no longer able to. And so it's a little investigation on that. And in particular, for independence proofs, we use a method which is known as the Frankel-Mostowski method of permutations or permutation models. And I was talking to people here at the conference, at the Cantor meeting. I've talked to people in other conferences in the US, and I'm surprised to know that many people do not know this method. So I think it's a good idea to advertise it, and therefore that's why I chose to speak about this. Okay, so there's gonna be a bunch of definitions. So for a set X, we're gonna say that X is finite. I guess you all know this one, if it is in bijection with some natural number. All right, so that one's pretty standard. I'm going to write another one, D-finite. So the D stands for Dedekind. If, well, if it satisfies what historically was Dedekind's definition of finite. So let me remember, because sometimes I remember a statement and then I need to put a negation on it. So D-finite would mean there is no function from X to X injective but not surjective. Right? And because it's going to be relevant, I'm going to write a couple of equivalences. So for this definition, equivalently, you can say there is no proper subset, which is equipotent to X. You can also say there is no injection from omega to X, or you can also say there is no countable subset of X. And now,
the first one can succinctly be written as X is not equal to X plus 1.
You can write that too. I'll add it there. I don't know how. Not. So I don't know if it's worth spending time explaining these equivalences. It depends on how much you know them. I assume this is pretty well known. It's very standard, and normally you would think that these two are equivalent. In one direction is obvious. All natural numbers satisfy this. But then if you just assume this and try to prove that there's a natural, well, if you assume that you are not Dedekind-finite, and you try to prove that you are infinite, no, the other way around. If you assume that you're infinite and you try to prove that the negation of this, the standard method is to say, well, since X is infinite, pick an X0. Since X is infinite, you can pick another X1. Since X is infinite, you can pick another X2, and so on. And that uses the axiom of choice. But right now, we're not even going to assume that. So if you just work in ZF, you have these two things, and they're different things. And there's other notions of finiteness. So these would be two notions of finiteness. There's others that have been studied by people such as John Truss, Paul Howard, Eleftherios Taxis. So I'm going to mention a few others that are sort of out there in the literature. And then I'm going to mention the ones that I introduced for this work. So another one that you can say, we call it A-finite. And the A stands for amorphous. So if you know what an amorphous set is, that's what it is. So X is A-finite if every time you can partition A into two cells, both cells are finite. I need to be careful here because there's, okay, I'm just gonna say if the only subsets of A are finite and cofinite. That's what?
It's called amorphous also.
That is in the literature called, well, technically amorphous is infinite plus you satisfy this, but that's what it is. So again, if you don't assume choice, these kinds of sets might exist. Any set of this sort is clearly Dedekind-finite because Dedekind-infinite sets, by virtue of their having a countable subset, you can partition that countable subset into evens and odds, and so it doesn't satisfy that. Another one that has been considered, well, the next two that I'm going to mention are sort of dual versions of B finite. So over here I talk about injections or an injection from and talk about surjections, and it turns out that if you dualize those two notions, they're no longer equivalent. So that gives rise to other two notions. C finite means there's no function. Okay, there's no surjection from X to omega. This is actually very annoying and it doesn't work too well. And it's equivalently the power set of X is Dedekind-finite. What?
Am I parsing three correctly? If every subset of A
Is either finite or cofinite.
if every subset of A
Or. This is an or. Right, okay, so yeah, C finite, these two things are equivalent. I'm just gonna show you, I'm gonna hand wave the easy direction. If there is a surjection from X to omega, then the fibers of that surjection give you a countable sequence of subsets, so that's a countable subset of this. And so the power set is Dedekind-infinite. And for the other direction, you have to play a little bit more, because you just assume that the presence of an infinite sequence of sets, and you have to do stuff to make it disjoint. But it can be done. And so this would be some sort of dual version of this over here. And the last one that I'm going to mention, E finite, if there's no function from X to X surjective, but not injective. All right, so I'm going to try to draw a little diagram here on this side. So those are my definitions. This is going to be my diagram. Locating all these notions. Finite is the weakest. Each and every one of these definitions, every finite set satisfies each and every one of these definitions. Okay. Finite implies A finite, and A finite in turn implies C finite, because if you were C infinite, there would be this countable sequence of, well, if you were C infinite, there would be this surjection onto omega. So just put together the fibers of odd numbers and the fibers of even numbers, and that partitions your set into two infinite pieces. And C finite in turn implies E finite. How does that go? If there is this surjection that is not injective, oh, I see. This one is actually interesting. I'm just going to draw a little picture. So suppose that you have from X to X this which is surjective but not injective. Then you can pull back, I guess for people who like category theory, there's some sort of contravariant functor going on there. You can get a mapping from subsets to subsets just by any subset here, just take the pre-image. The fact that this is surjective will imply that this is injective, and the fact that this is not injective will imply that this is not surjective, and it just works out. I forgot that I'm in a place where it's complicated to erase. I'm used to doing these little pictures and then just erase them quickly, because they only occupy a small portion of the blackboard, but apparently I need to be careful. All right, and all of these imply Dedekind-finite. And actually, none of these implications is reversible, and we will see that later in this talk when I explain the method of permutation models. Okay, so three more definitions really, but one that that was proposed by Horst Ehrlich, who was attempting to unify all these into part of one generic thing. So a class of sets is a finiteness class if it satisfies the following requirements. It's closed under subsets. It's closed under things that have the same cardinality. Cardinality here means they're equipotent, they're sub-ijection, because before someone complains that without choice, weird things happen. And then X finite implies X in F, and omega is not in F. So the idea is that the definition of finiteness class captures the notion of, oh, here's a definition of what could it mean to be finite. It's a bunch of things that it's reasonable to assume of finite sets. Subsets of finite sets should be finite. Same cardinality should be finite. This one is a little bit artificially there, but it basically prevents anything which is not Dedekind-finite from being there, because Dedekind-finite is, there's an injection from omega to x, and in particular, if there's an injection from omega to x and x belongs to the class, then omega should also belong because of these two properties. So this is there sort of like to exclude anything else, and you want to include all finite sets. Conceivably, there's other reasonable things that you could add here, like you probably would like the class to be closed under unions, but the problem is if you do that, you're excluding this one. The union of two disjoint amorphous sets is no longer amorphous. So Ehrlich and definition, and all of these satisfy that. Like I said, finite is always the smallest finiteness class. D-finite is always the largest finiteness class. And if you assume even something as weak as countable choice, then all of this collapses and you just have plain finite. So what I did, or this little summer project, was to introduce two new notions of finiteness that come from Ramsey theory. So more definitions, 5, 6. So I'm going to say that X is Rn finite. Oh, and maybe I should mention now, I'm going to do the same thing again, even though I'm going to have to erase later. Presumably everybody knows what Ramsey's theorem says here. I'm just going to write here the statement. Ramsey theorem says that if X is infinite, then for every coloring of the n tuples into two colors, there's an infinite Y such that the n tuples from Y are monochromatic. So if instead of X I write there omega, this is something that can be proved without choice. There's any of the usual proofs just goes through without choice, because you're just picking inductively your infinite sequence of things, and every time you need to pick the next one, pick the least such, and that's it. Now, if instead of omega I write here an arbitrary finite set, then in ZFC that's true for the very simple reason that if X is infinite, it has a copy of omega inside essentially, and then you just pull out the theorem there. But if you don't assume choice, that's no longer the case. So the definition over there is just going to take advantage of that, and we're going to think of a set for which Ramsey theory holds as a large set. And so if it fails, that's our notion of finiteness. So that's where this comes from. X is Ramsey n finite if there's a coloring such that for every infinite y this is not monochromatic. Now, how many people here are familiar with Hindman's theorem? Or maybe I should ask, is there someone who doesn't know what that theorem says? Okay, there's at least one is enough for reminding you of Hindman's theorem. This is another Ramsey-theoretic result. And it's usually phrased for omega, but I'm going to do the same thing that's for Ramsey. This says that for every coloring of all the finite subsets of an infinite set, right? There's many versions of it, and I explored various of them, but the one that I'm going to use for this talk is there exists a y pairwise disjoint such that all finite unions that you can get from these guys have the same color. So such that the set of finite unions of y is monochromatic. So this is just the set of all unions such that F is a finite subset of y. There's another version stated in terms of sums. So you can put here the natural numbers, and here it's the finite sums. But the finite unions version is widely used for many other things. So this is the one that I use. Once again, if instead of x here I put omega, this is something that can be proved without choice. Just the existing proofs, you can do them recursively. But if I put here now an arbitrary x, then that's not necessarily true without choice. And so I use that to define another notion of smallness. So I'm going to say that x is H-finite if the negation of that result, if there's a coloring such that for every infinite pairwise disjoint that's not monochromatic. All right. So I have to get rid of this now. So this gives me a whole bunch of definitions because I have H finite, I also have Rn finite for every n. Normally when you just work on omega and with choice, you can prove Ramsey theorem, for example, for pairs, and then from that you come up with a proof for triples and then for quadruples and so on. Without assuming choice, I don't think we're able to do that. I cannot prove it yet, but I don't think you can do the same sort of inductive argument. And in general, between the different Rn's, if I don't assume anything at all, then I have no idea what goes on. So I'm just going to mention one little result with an extra assumption. So proposition. So if x is linearly orderable, and Rn finite, and then x is Rn plus 1 finite. So just in ZF, sets might not be linearly orderable, but you can add, for example, a weak choice principle that says every set is linearly orderable, and that is consistent with the negation of countable choice, for example. So you can still assume that everything's linearly orderable and still be in a world where these haven't collapsed.
Linearly orderable follows from the autofilter theorem, right? From the Boolean prime ideal.
Yeah, it follows from Boolean prime ideal theorem. Yeah. which is another thing that doesn't imply countable choice. So you could also assume something like the Boolean prime ideal theorem and still productively work with these. What you don't want to do is assume DC or any of those things that people like, because then that trivializes my diagram. Okay, so proof. Let's just assume that X is linearly orderable. Let's suppose that it is Rn plus 1 infinite, and I'm going to show that it is Rn infinite. And basically, it's just going to be the usual proof that you do for omega, and I just need linearly orderable to make it go through. So I'm assuming it's Rn plus 1 infinite, and I want to show that it's this infinite, so I take an arbitrary coloring. Now define another coloring of n plus 1 tuples, just mapping every finite set to C of A minus its minimum. That defines a coloring on the n plus 1 tuples. It makes sense to take minimum because X is linearly orderable, and well, each of these is finite, so being linearly orderable, it will have a minimum. And so find Y infinite with its n plus 1 tuples D monochromatic. And so essentially Y is going to be n monochromatic too, because, well, if you give me any two tuples, any two n tuples from Y, just look for another point to the left of them, and that gives you these two n tuples become n plus 1 tuples with that point adjoined, and they have the same color because of this. And so if you remove the point, they had the same color according to that. The only sort of little issue with this is you need to be able to pick a point to the left. So I'm just gonna let Y prime be either Y if Y has no minimum, or Y minus its minimum otherwise. And then it works. So then Y prime of n tuples are C monochromatic. Was that argument clear, or did I lose people? Yeah, okay. All right, so without assuming anything, I really have no idea what happens with the Rn's. Assuming something like the Boolean prime ideal theorem, I can figure that there's this implication R2 finite implies R3 finite and so on, but nothing more. I will show later that these arrows are not reversible though, so at least I have independence results. But in terms of just direct implications, this is as much as I could get with the Rn finites. Something much more interesting happens with the H-finites. So let me write a theorem.
Excuse me, so instead of what, it would be enough to choose from every finite set to have a function that chooses an element from each finite set, right? Or is it not, but no. Okay, never mind.
For this, but you would need to choose it in a very uniform way. So that's what the,
yes. That's
Mm-hmm.
the end of the proof. You need that it's always
that is always the same. Yeah. Okay. For H finite, something much more interesting happens, I think. So let X be a set, but since everything is a set, I don't need to write B a set. So just let X be. The following are equivalent. X is H finite so what I'm going to write here is basically H finite, but not for the full Hindman's theorem where you take all finite unions, but just the one where you just need to take pairwise unions. So, or not unions of at most two things. So there exists a coloring from finite sets to 2, such that for every infinite pairwise disjoint Y. Oh, actually, this one over here is wrong. These need to be finite sets. So instead of all finite unions, just unions of at most two things. The coloring of this, it hits at least two colors. And 3, the finite power set of X is Dedekind-finite. I always get confused with working with these because I need to remember when to put a negation and when not. It's easier to deal with the negations of these. So right beside, I'm just going to write the negation of each of these, and those are the ones I'm actually going to use in the proof. So 1 prime, X is H infinite, so which means Hindman's theorem holds for X. 2 prime, for every coloring, there's an infinite pairwise disjoint family so that the unions of at most two things are monochromatic. So Hindman's theorem for unions of less than or equal to two things. Is there a name in English for the things that you are taking union of? Like when you do a summation, each of the terms is a summand. When you do a product, each of the terms is a factor. When you do a big union in Spanish, each of the things is un uniendo. Is there something like that in English? No? Okay, things is fine.
Summand is fine here.
Oh, okay. Could be summands, yeah. So for unions that are... no, yeah, I'm always assuming pairwise disjoint.
It's really a sum.
It really is. You're right. Hindman's theorem for unions of at most two sums. Yeah. And if it's an intersection, every term is an intersectando. And 3 prime. Okay, so I'm going to be more explicit. The finite subsets are Dedekind infinite. That just means the set of finite subsets has an infinite, a countable subset, or an injective function from omega into it, which is the same as saying a countable injective sequence. So there exists something like this. Okay, so those 3 things are equivalent. So let's prove it. Proof. Obviously, 1 prime implies 2 prime. This is a weaker statement a priori. So that's just... I'm going to do 3 prime implies 1 prime first because it's slightly easier than the other. So for 3 prime implies 1 prime, right? So let's assume that I have my injective sequence of elements. Let's prove that Hindman's theorem holds for X. The first thing to notice is that I have my injective sequence of finite sets. There's nothing there guaranteeing that they be disjoint. But you can always wiggle around and make them disjoint. So let me write this down and then explain how it's done. So let Xn and an omega be what you need it to be, injective sequence of elements. From there, build a pairwise disjoint sequence of yns. How do you do this? Y0 is just x0. And then that's finite, so it only has finitely many subsets. However, there's infinitely many things here. So eventually, there's one index such that the corresponding thing is not a subset. And so just take the difference, and that's your y1. Now this union is finite, finitely many subsets. Eventually, one of these is outside. Take that difference. And that's how just using this and without using any choice whatsoever, you get a pairwise disjoint sequence out of that. So you have a bunch of pairwise disjoint finite sets. And now what I'm going to do is I'm just going to, so consider a function from finite subsets of omega to the finite unions of the y's, just mapping each f to the union of the y's n in f. And that's the end of the proof. I'm going to explain why that's the end of the proof. This function is, well, it's a very nice function. It is bijective. It is, in fact, a homomorphism. If you think of taking unions as some sort of group operation or semi-group operation, the union of those two things here, especially the union of two disjoint things here, gets mapped to the union of the corresponding things there. And what that means is that if you give me any coloring of x, of the finite subsets of x, I restrict the coloring here, and composing it with this function, it gives me a coloring of omega to the less than omega, for which we know Hindman's theorem holds. So I get my infinite monochromatic set and just pull it back here. So that's it. It was just a matter of showing that x has something inside which is isomorphic to this. Okay, and now let's, the one that's missing is 2' implies 3'. Okay, so for 2' implies 3', let's assume that Hindman's theorem holds for union of at most two summands, and I'm going to try to come up with an injective sequence. So what I'm going to do is I'm going to use that Hindman's theorem holds, so I'm going to use a special coloring. So consider the following coloring. Okay, and you're going to complain that since there's logarithms, maybe this is calc 1. But no, this is actually something very simple. This is a finite set, so I'm doing this to its cardinality. All right, so you give me a finite set. It has a cardinality of some finite number, and you can write down that finite number in binary. Maybe it's something like this. So taking logarithm of base 2, the integral part of that, all it's doing is it's telling me what's the position of the last one. So for example, this number 0, 1, 2, 3, 4, 5, 6. This logarithm base 2 would be 6. So all it's doing is it's just telling me what's the position of the most significant digit in binary, and then just is that position even or odd. So that's all I'm doing. I'm just coloring sets by that. And so by assumption, there's an infinite pairwise disjoint family such that all the members of the family plus all the unions of two elements of that family have the same color. Such that, so I guess I'm going to write it like this. Finite unions of at most two things. Okay, and so now what I'm going to argue here is that within this family, any two distinct elements must have different cardinalities. Why is that so? So notice that the cardinality mapping from y to omega is injective. Because if it wasn't, if you had two sets y and z with the same cardinality, when you consider, so that cardinality is a number which has a parity when you take this logarithm. Let's say that my number is this thing in binary, for example. So let's say that this is the binary expansion of cardinality of y, which is cardinality of x. These are getting a color, which means that this position is either even or odd. And now when I look at the union, that's supposed to have the same color. But since x and y are since y and z are disjoint, then the cardinality is just, well, this cardinality plus that cardinality, and it's the same cardinality, and so it means it's just this number times 2. But in binary, multiplying times 2 just amounts to putting a 0 here, therefore exactly changing the parity of this significant digit. So, if y and z had both the same cardinality, then their union would have a different color, and so that cannot happen. So the cardinality mapping is injective, and therefore you can easily from here build an injection from omega to y. because that's just, well, look at the range of omega. Sorry, look at the range of this mapping. That has an increasing enumeration, and so just appropriately compose the inverse of that with the inverse of this, and that's how you map injectively omega, in fact, bijectively, omega onto this y. And in particular, omega is mapped injectively onto here. Okay, let me see. All right. All right, any questions so far? No? Corollary of this. H-finite implies C-finite. The other way around. It's implied, no. Yeah, the negations are, having to negate things is very complicated. Okay, yeah, H-finite is implied by C-finite, and the easy way to see that is to take the contrapositive. If you are H infinite, then your finite power set has a countable sequence, and in particular, that's a countable sequence of subsets. Just forget finite. So you are C infinite. So my diagram now starts looking a bit. So here's H finite. So these are implied like that. And I'm going to put all the way here the Rn finites. Which among them, as far as I know, there's no relation. And there's no relation also either between these and those. So I think this completes my diagram. This exhausts the just straight implications that I can prove. And now I'm going to explain the method for proving that all of these are independent, that none of these arrows is reversible. So I'm going to keep my diagram and my definitions. And I'm just going to work for the rest of the talk in this one.
Can we now assume something in the general context, like everything is linearly orderable?
So, well, for this proposition, you can assume that, and it gives you a chain of implications. For all the others, I'm not assuming anything. And for that diagram, I'm not assuming anything. So it's just ZF, plain ZF. You have all these implications, and then in plain ZF, I'm going to show that they're not reversible.
You know, so there might be additional questions like, you prove one thing doesn't imply the other. Is it consistent jointly with everything?
For example, amorphous, I think if you have the linearly ordered set, it cannot be amorphous, right?
Let me think.
You can split it linearly ordered always in two pieces, and so you have those things at the top where above they're only finitely many, there are those at the bottom where below they're finitely many, so I've just split it into top and bottom. Unless there are always only finitely many predecessors, but then you have a map onto mega, like counting the predecessors. So if a set is linearly orderable, then finite and amorphous means the same. Finite and afinite means the same, for example.
At some point, I followed the gist of it, but not the whole thing, but it sounds plausible, so I'll trust that. But yeah, but for example, for the RNs, all I have is this implication. It requires you to assume something, and I'm going to show that the reverse implication cannot be proved, but I still don't know if I can show that independence result together with the linearly orderable principle, for example. So that's...
Your counterexamples will be sets of reals.
No, there will be something...
No, that's not yours. I meant sets of reals.
I suppose you can probably think of them that way, but...
No, but he wants to do Mostowski models, right? So
yeah, so they're just going to be atoms.
In software, they might be translatable, but maybe not to set, maybe at a higher level.
Yeah, I think it depends how far you need to go, which for these things is not going to be very far, but it does depend.
So at the end, you have a model for that. So we said that
No, he constructed a model of CF with atoms, right?
Yeah.
But you can embed that in the model.
Well, yeah.
Yeah, but the question is where can you embed?
Yeah, the question is why.
V omega plus 2.
For what I'm going to do, it probably is, but But the truth is that I never looked at that in detail because I mostly just black box the transfer theorems of Pincus. But I know that they're proved that way. Yeah, I don't do the last step. But I know how it's done. So it's plausible that v omega plus 3 at most suffices, but I cannot say for sure. Okay, so for the independence proofs, yeah, I'm going to use this Frankel-Mostowski method. And so for that, I need to explain what's ZFA. So there's ZFA, and I suppose there's also ZFCA. And the A just stands for atoms. So these are, well, this is another theory. It's not the ZF that we're all used to. So it's ZF and ZFC with some small changes. So first of all, the language changes. So usually in set theory, we just our only non-logical symbols. It depends how you think about it. But basically, the only non-quantifier Boolean connective variable symbols are these. In ZFA, we're also going to have symbol for the empty set and a special unary predicate, which is basically supposed to mean these guys are atoms. Oh, I should say something about the intuition first. So the idea is that this is a theory in which we're going to have atoms, which are what one would normally think of as elements of sets that are not themselves sets. They're like things that are at the very bottom. They're allowed to belong to other stuff, but they themselves don't have elements. And even though they don't have elements, they're not all equal to the empty set. So that's the idea. So you're going to start with some set of atoms, which in some other contexts are called your elements, and then from there you build your set theoretic universe. So the language includes a unary predicate for atoms and a symbol for the empty set. And, well, so axioms. So like those of ZF, except a few axioms change. For example, the empty set, normally you just say there exists an X that has no elements, but here you need to be more explicit because all atoms are not going to have elements. So you need to say this symbol has no elements. Another axiom that changes is extensionality. Because if I just write it the usual way, then the consequence would be that all atoms are equal among themselves and equal to the empty set. So you don't want that. So extensionality is just restricted to things that are not atoms. So for every X which is not an atom, for every Y which is not an atom, then extensionality holds. But it has those restrictions.
A is a predicate, A is not a set.
Well, yeah, such that A, yeah, but we all know that we mean this.
You might have a class. Maybe you want to set it.
It depends. For all the, for what I'm doing, a set of atoms suffices. Yeah. Oh, that's a set of, no, there's models where you need the set.
So A could be a constant.
A could be. No, I think it's a predicate anyway. It's just a unary predicate.
Then you can demand that there is or there is no set which has this extension.
Yeah, exactly. I think that's what happens. So I guess, yeah, maybe I should be explicit and write this down. There's an X such that for every Y in X, if and only if Y in A of Y. And then from that point on, I start abbreviating like this. So for all the models that I'm going to consider, this holds. The set of atoms is really a set. But I know there's some weird models that have been used to prove independence of some more complicated things where they do it in such a way that the class of atoms is in the end a proper class. So, okay, I don't know. This is optional for now. What other thing changes? Foundation. Again, just same thing, but just restricted to things that are sets as opposed to atoms. Okay, and so, well, these are the small changes. Other than that, the axioms are just like the usual ZF axioms, and choice is just phrased like the usual choice. And oh yeah, no, definitely, I need that. Yeah, there's another axiom here that I missed in my notes, but also let's just call it the axiom of atoms, which says for every Z, yeah, so atoms don't have elements.
I don't understand why foundation changed. What are you worried about with foundation? Foundation says what? That
Foundation says
empty subset
Empty set has a minimal element.
has an element which is disjoint from it.
mm-hmm.
But the atoms are not non-empty.
Atoms are empty, yes.
I guess it depends on how you phrase it. So you can just say for every x, if x has an element, then blah, and then it doesn't change. Mm-hmm. But if you're used to phrasing it as for every x different from the empty set, then now you need to be careful. Because what if x is an atom? So yeah, I suppose it's just that little technicality. So, okay, so you have these other axioms. So this gives you a different system. But if ZF is consistent, then this guy is consistent. Or if ZFC is consistent, then that guy is consistent. And I'm not going to go into the details of that. But basically, the idea is to just choose a set which is high enough in the Zermelos hierarchy and decide that you're going to interpret that as atoms, and therefore you never ever take anything below into consideration. You just pick a distinguished element and decide that you interpret that as the empty set, so that the actual empty set doesn't mess up with your stuff, and then you just look at the hierarchy above that. So that's not too complicated. So I'm not sort of, this is not like a large cardinal thing. This is, if ZF is consistent, I can consider this and there's no problem. And
You still have a V hierarchy, a V alpha.
Yeah. Yeah, so I'm gonna say that in a second. So there's a Zermelo hierarchy. Oh, and just in the spirit of saying obvious things, if you take all these axioms and add an axiom that says A equals empty, then you get back your old ZFC. Is this a Y or an I hierarchy?
I.
Yeah. Okay. So there's a well, I've always known it as Zermelos cumulative hierarchy, but it could be von Neumann. Von Neumann proved that foundation is consistent by using the hierarchy.
Whereas Zermelos, they would be the Z alpha, it's not the V alpha.
Oh, I never thought that B was for von Neumann. I always thought that B is because the universe literally looks like a V. Yeah, couldn't probably, or the rank. I mean, the proof that foundation is relatively consistent with the rest is von Neumann, just using the hierarchy. So, okay, anyway, so there's a Zermelo hierarchy just with small changes. So I'm going to call it V0 of A is just A, V alpha plus 1A. Things are no longer as nicely transitive as usual, so you need to explicitly add the previous stuff and then take power set. And limit stages are the same as usual. Okay, so there is a Zermelo hierarchy. And now the method here for obtaining independence proofs is basically, well, the set of, when you look at the set of atoms, any two atoms are more or less indistinguishable. You're going to start introducing new symmetries to have a finer distinction of which atoms are indistinguishable and which ones aren't. So this is always done by means of permutations. So suppose that I have a permutation of the set of atoms. So I'm just permuting the atoms, and the idea is that I'm going to use that permutation to induce a permutation of all sets in the universe, just in the usual recursive way. So pi induces an isomorphism of the universe when you have that set of atoms defined in the usual recursive way. So X is just so you permute the atoms, and that accordingly induces a permutation of all sets of atoms, which in turn induces a permutation of sets of atoms, and so on. You just climb up the hierarchy. So every permutation of the atoms induces one of these things. And it's really an isomorphism. So like pi of x belongs to pi of y if and only if x belongs to y, and the same for equality, and the same for like when you evaluate a function, pi of f evaluated at pi of x is the same as pi of f of x, and everything goes through the same, the way some of you are probably used to when with elementary embeddings, for example. Yeah, that's true. So induces an, I'm gonna see, yeah, this is L, so that it can induce that. Yeah, everything stays put, the empty set stays put, and so on. All right, so, okay. So this is when I consider a single permutation, but interesting things happen when you start considering various permutations at once. So from now on, fix a group of permutations, a subgroup of the group of all permutations of atoms. And so this is, I guess, technically a definition. And I'm not going to mention G, but G is going to be omnipresent in what I say next. So this definition will depend on G. I change the G, it changes things. So what do I want to define? As support. So, okay, let X be a set, but I don't need to say set.
Let X be.
And let F be a subset of A. So we say that F is a support of X if the following happens. If for every pi sigma in my group of permutations, if pi does the same as sigma in F, then pi moves X to the exact same place as sigma. So in other words, the support is, so when you have a set in ZFA, you can compute its transitive closure. So the set is somewhere here up in the hierarchy, and you can look at all the atoms that are ultimately involved in its construction. But even that might be too much. Maybe you don't need to know all the atoms in the transitive closure. The notion of support is these are just enough atoms so that if you know how I'm going to permute those, I already know what's going to happen to X. Another way, if you just do the algebra, there's another way of phrasing this. So equivalently, for every pi that fixes F pointwise, pi will fix X. Yeah, so you can just do the usual, just couple of algebraic operations and see that this is equivalent to that. This is the one that we're going to use more frequently, but we need to be careful. Pi needs to fix X pointwise. I'm saying it doesn't move any of the elements of F. It only fixes X setwise. I mean, it's possible that it still permutes all the elements of X somehow, non-trivially. The only thing I'm demanding is that permutations with this, they don't need to fix X setwise, sorry, pointwise. They only need to fix it setwise. So all I'm demanding is that elements of X get still mapped to elements of X. But setwise, not pointwise. No. So think, for example,
X is in the fix of pi or whatever it's called.
Yeah.
If F is a subset of fix of phi, sorry, if F is a subset of fix of phi, then X is in fix of phi.
If F is a subset. Okay, yeah, but when I read it that way, my mind just goes in circles because I need to, there's subset here, element there, and there's the same fix.
Support is much smaller in general than, say, looking at the transitive.
Yeah, the support is in general much smaller, yeah. For example,
The support of A minus A0 is just A0 itself.
it depends on what the group is, so we need to be careful that this definition is taking the group into account. There's a quantifier here over the group, so these things will depend. But maybe instead of going further with my just abstract explanation of this, I can introduce my first example so that these things start making sense. So first example is what's known as the first Frankel model. So example. Well, I haven't said how you define models, but I'll get to that. So for now, this is going to be an incomplete example. I just want to make the point that you can, for example, the easiest subgroup of the symmetric group is just pick the whole symmetric group. So what happens when I decide that my group consists of all possible permutations, right? So how do these definitions play out? If this is my set of atoms and I have something like a point x here and I look at A minus x, right? So this is a big set. If you look at what atoms are involved in its construction, it's basically all of them but one. However, singleton x works as a support for this because any permutation that fixes x here pointwise, well, it might permute everything else, but set-wise, it's still fixed. So has x as a support. Okay. I'm running out of Blackboard, but I guess we can probably forget about this. Oh, can I use that? People were, oh, and then the camera. No, I'm just going to erase this little column. I can finish here. So once you have this theory of ZF with atoms and you have a subgroup of the group of permutations, you can start defining what's known as the permutation models. You can go in more generality, but I'm just going to use what I need for the results that I'm going to present. So this is just a very particular case of permutation models. But the idea is as follows. So again, definition. So given a group of permutations, X is said to be symmetric. And so again, this definition depends on the group. If I change the group, I change what things are symmetric if X has a finite support. And again, remember that the definition of support depends on which group I fixed. So symmetric sets are just going to be those for which you can find a finite set such that any permutation fixing each of those points will fix X set-wise. For example, with this group, this set is symmetric. It has a support which is finite. And so the key thing here is that, well, I suppose this is something that everybody here knows in this room. Whenever you have a class, you can also form the class of things that are hereditarily of that class. And so when you do that with symmetric sets, so you look at all the hereditarily symmetric sets, and that's going to be a model of ZF. So the important theorem, which, well, I'm going to attribute to Frankel-Mostowski, but the story is more complicated than that. No, Polish names never end in Y. Okay, For every subgroup of the permutation group, the class of hereditarily symmetric sets I should be careful and not say sets. Hereditarily symmetric elements, I'm going to say. Because atoms are always symmetric, pretty much by definition. They always have themselves as support. So atoms are always symmetric by definition. But so the class of hereditarily symmetric stuff, W, is such that W satisfies ZFA, right? So that's how I get myself. It's a submodel of the full universe, and in most cases, this W will not satisfy the axiom of choice. And so that's the first important theorem. I'm going to say theorem 1, which allow us to get models of ZFA. And by playing with the group of permutations, you can play with what statements are true in that model. And then the next question is, all right, so fine, you're proving independence of something in ZFA. What are the implications of that for ZF? So important theorem number 2 is going to say that if you can do this, then you can do it in ZF. So important theorem. There's actually a full family of important theorem 2s, which are known as transfer principles. Statements that say if you can prove such and such, or if you can obtain such and such model, Frankel-Mostowski model satisfying these statements, then you can get a ZF model satisfying those statements. So I'm just going to mention the one that I'm going to use for today. So this is due to Yeh and Sohar. And it says that, so if you have a model with atoms that satisfies choice, this is important. Typically, I assume choice in my full universe, and that's used non-trivially in various arguments to make sure that there's enough permutations for doing stuff. But then in the submodel, choice is not going to hold. So Yeh-Sohar says that if you have a model of ZFA and some subgroup of the group of permutations, and W is the class of all hereditarily symmetric stuff, okay. Then for every ordinal alpha, there is a, I'm going to say here, symmetric extension. For those of you who know what that is. For those of you who don't, it just says that there's a model of ZF satisfying such and such things. So W prime such that, no. Oh yeah. And a set B in W prime such that all the sets in my universe with atoms interpreted according to the hereditarily symmetric. So in my submodel, I look at all the sets of rank at most alpha, and they behave exactly as they would if you iterate the power set operation alpha many times on this B here. I should say here, W prime satisfies ZF. And this is according to W prime. So this is a very restricted transfer principle. It says, well, every time you can come up with a permutation model that satisfies something that has to do with either the atoms or the set of atoms or sets of atoms. So, but there's a bounded place on in which all of the things that you consider live, then it's possible to find a model of just plain old ZF with no atoms and a set there that behaves exactly the same way. So this is all I need for my independence results here. If I produce a permutation model, for example, with a set which is H-finite but C-infinite, then this theorem tells me, well, you could have produced the same also in just plain ZF, and therefore showing that the arrow is in fact not reversible, whether or not you use atoms. So those are Yeah, so these two are the ones that make all of this over here important. And so I think these are all the tools I need. Yeah, question.
So the hypothesis is V of A is a model of Z of C A.
Yeah.
And that's the A that you use.
Yeah.
D is a subgroup of the symmetric group of A, and W is the hereditarily symmetric.
Yeah, these A's are different A's, if that's what you're asking.
The W you build over.
Yeah. No. So the W is the same construction here. It's first take a subgroup of the permutations of the atoms.
But that A is the one that you use as the interpretation of a constant.
Right. Yeah. So this is not just an arbitrary set. This is the set of atoms. So it's when I do constructions where in my symmetric extension, the set that I'm looking for is usually the set of atoms, but I'm gonna, if time allows, now that I'm looking at the clock, one of my things to show one of these independence results is a set of sets of atoms. And in fact, it's for every alpha. So every time you produce a proof where the thing that you get in your symmetric model is just bound, you only care about one set, or you only care about a bunch of sets that you can bound by rank, then you can do it in a model of ZF. Things like the linearly ordered principle, for example, or the Boolean prime ideal theorem, those are statements that say for every set of some sort, there's this other thing. Those are much harder to transfer because those are not bounded like this, right? If I say for every set, there's a linear order on that set, well, that's for every set of any rank. So that's why when you consider independence of statements with things like the linearly ordered principle or the Boolean prime ideal theorem, then it becomes harder. And you need to look at other transfer theorems or really get dirty with permutations and how they play with the rank, but those are much more complicated proofs. These ones are comparatively easy. I just need to show.
What does this relation that's written like isomorphism mean?
It means epsilon isomorphism.
Uh-huh.
Yeah.
Okay. So it's a very strong copy of.
Mm-hmm. Yeah, I mean, it behaves in exactly the same way when you look at B and its power set and so on.
Maybe this is insufficient what you're doing, but typically these things are done without atoms, they're done with names. So you have a P-generic extension choice, and then you look at the hereditarily symmetric names.
Yeah.
And then form the choiceless inner model generated by the hereditarily symmetric names with respect to some subgroup of the some permutation group of the Boolean algebra.
Yeah.
Yeah. But I mean, that's a way of going direct, or the same within set theory. You're not going to atoms at all in that approach.
Yeah.
Perhaps is it not sufficient for what you're doing? I mean,
it probably is, but I mean, so there's two things to be said about this.
In that case, you're always doing inner models of forcing extensions.
Yeah.
Here you don't seem to be doing that. Right?
No.
I mean, technically, it's easier to do. I mean, Mostowski was before Cohen.
Yes.
So it's, I think a permutation model can be more easily understood. You don't have to know forcing to understand.
Right.
Exactly, that's the point.
And then you can say, well, whatever I did here, I might be able to transfer to a forcing argument also.
Right.
Yeah.
In Zucker, there's forcing hidden there.
Oh yeah, no. There's forcing done here. Yeah,
Right.
so this is a symmetric extension, which is, but I'm just black boxing it. There's something to be said about the pedagogy of this. Remember, this is an undergraduate research project that I did with some undergraduates. They were able to understand this in a couple of weeks, and they were doing permutations, and we were proving independent stuff. If I had tried to teach them forcing, well,
yeah, that would take
that would have taken a couple of years. So that's the main reason. And I also think that it's interesting. For certain things, it might be easier to think about this than, I don't know. I don't have too much problem thinking about forcing, but forcing first and then going to a submodel certainly seems a bit more complicated than just doing this.
Clearly here you want the atoms to form a set, right? Otherwise you're not going to get this.
Yeah. So I think this is for, yeah.
Will not be a proper class.
Yeah, I think you need to be careful with, I mean, there's many variations of this. You can have A be a proper class. You can, well, this is the easiest way of creating symmetric sets. I just demand that they have a finite support, but you can replace finite with belongs to some ideal, and you can add extra conditions. So when you really want to get into doing independence of many different things, people have had to come up with many non-trivial variations of the method. And then some of these theorems will not go through. They have to prove them again, and so on. Okay, anyway, so let's go back to the first Frankel model. So my group is all permutations. And, well, I pointed out that if you have an atom, first of all, it is symmetric because it has itself as a support. Any permutation that fixes X, it fixes X. I'm actually going to write A here because X to me is always something with elements, and I'm going to get confused otherwise. But also, the complement of A, everything else, is also symmetric because it still has that singleton as a support. Any permutation fixing this will fix setwise the complement. And this goes through, in fact, for every finite set. So every time I have a finite set here, the finite set will belong to the symmetric, to the permutation model because it has itself as a support, but also its complement. So F is in W. For now on, W is going to be the collection of hereditarily symmetric things. So F is in W because it has itself as a support, but also its complement because it has F as a support. Any permutation fixing these pointwise will fix the outside setwise. So, okay, we're already starting to get to the point where interesting things happen. Here's my set of atoms. I already argued that every finite set is in the model. Every cofinite set is in the model. It turns out that nothing else lives in the model. And this is going to show that in this model, my set of atoms is A finite. You cannot partition it into two infinite pieces. And why is that the case? So suppose that I partition A into two infinite pieces. I'm going to show that the pieces are not hereditarily symmetric. And that's very easy. If they were symmetric, they would have a support. And that support would be finite. Oh, I should have said at the beginning. So I guess I start with a set A, which is of the same cardinality as omega. So that's what happens in my ambient space where choice holds. A is in bijection with omega. Then I look at this group, look at the hereditarily symmetric things, and suddenly that bijection with omega disappears. It's not symmetric. And no infinite co-infinite set can be symmetric because, like I said, if it was there, there's this support over here. And so in theory, every permutation that fixes these points should fix each piece of the partition setwise. But it's very clear that you can always come up with permutations that fix this, but exchange these two, for example. And that's it. Permutations fixing this, but not fixing this half or that half setwise. And that shows that those halves are not symmetric. So A, I'm going to write it like this. W satisfies that A is A finite. All right. Since the set of atoms in that model is A finite, it means it satisfies all these definitions of finiteness. In order to have full information, I just need to know whether or not A is Rn finite. And in this case, it's going to turn out to be infinite. So I'm going to write here and Rn infinite for all n. And why is that? So what I'm claiming here is that within this model, Ramsey's theorem holds for the set of atoms. So I need to start with an arbitrary coloring. I'm just going to do it for pairs, but it's the same idea for n tuples. So suppose that I have a coloring. And by this, I mean W has the coloring, so the coloring itself needs to be hereditarily symmetric. So the coloring has a support. Let's call it F. That means every permutation that fixes these points needs to fix the coloring setwise. So let C be an element of a symmetric set. Let F be a support for C. So I claim that A minus F is monochromatic. In other words, if you take any pair of points here, they all have the same color. And why is that so? If I take a pair of points here, x, y, and another one, x prime, y prime, right? My group is the full permutation group, so clearly I can come up with a pi that fixes this but maps x to x prime and y to y prime. And what that means from the perspective, so the coloring has in itself an order pair that maps x, y to whatever color they have, right? This is an element of C. Any permutation that fixes this pointwise should fix this setwise. So a permutation that maps x to x prime and y to y prime maps this guy to x prime, y prime, I. And notice that I doesn't change because I is just, I mean, it's either 0 or 1. That's a very simple set. And in general, what happens is this is what's known as a pure set. It has no atoms in its transitive closure. Those are always fixed by any permutation. So this permutation maps this pair to that pair, and it fixes the support. So this pair should still belong to my coloring, which means that this pair is mapped to the same color as this pair. And that's for any two colors. So this complement is monochromatic for that coloring.
Alternatively, instead of using the Frankel model, there is this notion of strongly amorphous set, which means not only is every subset of A finite or cofinite, but every relation is definable in the language of equality, confined to many parameters.
Oh.
This is strongly amorphous. And the
okay.
Amorphous. And if you're definable from finitely many parameters, then if you take the parameters into your support set, then everything else is essentially constant.
Yeah.
I mean, so you don't have really many coloring functions. That's the point.
Yeah, the point is that, yeah.
From finitely many parameters, and everything else it has to be, in this case, constant.
Yeah. Okay, so the moment that I was waiting, so the first Frankel model shows that this implication is not reversible, and no. And this one over here is not reversible. This doesn't imply that because it's this infinite. So this is atoms in first Frankel model. Okay, next example. Why should I get rid of? Okay, I will try to keep the definition of symmetric in this, and I'll get rid of everything else. Okay, so another model is quite surprisingly known as the second Frankel model. And so this one goes as follows. I have my set of atoms. Again, it's countable in the real world. And what I do is I partition it into countably many pairs. So in my mind, I always have it like this. It's a sequence of countably many pairs. And so the permutations that I'm going to allow are just that might or might not flip a pair, but other than that, they don't do nothing. You cannot map an element from here to an element from there. You cannot do any of that stuff. My group of permutations is just, all it's allowed to do is for each pair decide if it flips it or not. So G would be all the permutations such that they fix set-wise each pair. Let me see what. Okay. Right. So this gives rise to another permutation model. The same thing, you need to have finite support, but now finite support means a different thing. It means a finite set such that every permutation from these ones, fixing that set pointwise, needs to fix the whole thing setwise. So for example, we can see in this model that the sequence of pairs, the mapping that maps n to Pn, that is symmetric. That has empty support. Any permutation, when you apply it to the elements of that mapping, they look like this. Right? Hold on, no. They actually look like this. I mean the mapping that maps n to Pn. So it looks like that. And so no matter which permutation I take, it's subject to this requirement. So it's going to map n to itself because n is a pure set. And it's going to map Pn setwise to itself because it might or might permute the two elements. But overall, this guy stays put. So the sequence of pairs is symmetric. And in the symmetric model, this sequence lives there. There's no infinite subset of omega so that the pairs with those indices have a choice function. That's impossible in this model. If there was such a choice function, right, choosing infinitely many points from, well, choosing one point from infinitely many pairs, that function would have a finite support. Okay, forget the support, go far enough, and then just pick a permutation that fixes every, and pick one of the supposedly chosen elements, pick a permutation that fixes all of these points but flips this pair. And that's it. When you apply that to the function, suddenly it's no longer choosing this point but that point. So that was not symmetric. And this is important because this is going to allow us to prove that the set of atoms here is Rn finite for every n. Because you can now use the usual trick that you're probably familiar with. Let's color pairs, and this works for, again, for any n tuples, for any n, but let's just look at n equals 2. Let's color pairs of atoms as follows. You color them red if they belong to different pairs. You color them blue if they are in the same pair. And it's impossible to have an infinite monochromatic set because if it was monochromatic color blue, that would require to have an infinite subset within a pair, which is impossible. So it has to be monochromatic with color red, but then that means that no 2 points can belong to the same pair. So that was actually one of these choice functions that we said cannot exist. So that's how you come up with a bad coloring here. So this is Rn finite. And what else it is? H infinite, but E finite. Okay, let me think about that. Why is it H infinite? It's H infinite for the very simple reason that I just mentioned. The mapping that sends n to Pn is actually a symmetric thing. It lives in the model. So that is your countable sequence of finite sets. We said that that was one of the equivalences of H finite, H infinite. And H infinite. And then I said A finite? No, E finite, yeah. Why is it E finite? Let's remember the definition. So to show that it's E finite, I need to take an arbitrary function from A to A, assume that it's surjective, and prove that it needs to be injective. So suppose that you have a function here from A to A. Let me clean up my picture a little. Okay, so again, that means assume that there's such a function in my model of hereditarily symmetric stuff. So that function needs to have a support, and the support is finite. And according to that function, these guys get mapped somewhere, and maybe some other guys get mapped here. But after finitely much time, I'm done, and I'm left with stuff that has no influence with the support. And then let's see what happens to an arbitrary element that lives there. So this guy, where is it mapped? It cannot be mapped to a different pair, because if it was mapped to a different pair, it's very easy to come up with a permutation that fixes everything up to here and then it switches these two. And so suddenly the function is mapping this guy both to this guy and to that guy. So that cannot happen. So therefore every point needs to be mapped within its own pair. It might stay put, it might get flipped, it doesn't matter, but that's how the mapping works. And that's how it works in a cofinite set. And so then in the finite set, it still needs to be surjective, and for finite sets, surjective implies injective. So that finishes the proof that my supposedly surjective map had to also be injective. No, this is E finite. No, this is E finite, yeah. If you're surjective, you must be injective. So that gives me more to put in my diagram. The set of atoms in the second Frankel model separates Dedekind, it separates finite from R finite, because it's R finite but infinite, and H infinite, and E finite, so like this.
H and E have to be on different sides.
What?
H and E should be on different sides of the line.
Oh, it's E finite, yeah. Okay, so as you can see, once one explains the machinery, these things become very, not just very simple, but also a lot of fun. So let's just do one more model. Okay, this was my explanation of second Frankel model. So there's another model that I don't know if it has a name. I don't think it has a uniform name. So I'm just gonna call it, I'm not gonna call it anything. I'm just gonna say example 3. So it's going to be a lot like the second Frankel model, but instead of pairs, I'm going to deal with infinite sets. So in this case, you start with your atoms partitioned as countably many infinite sets. And the same thing. I want permutations that only permute each of the ANs, but don't mix them up. All right, so what happens with this model? So in this model, you again look at the symmetric sets. W satisfies A is, okay. First of all, the same argument over here to show that the mapping that sends N to Pn is actually symmetric. Over here, the same thing works. The mapping that sends N to An is symmetric, and therefore, my set of atoms will have this infinite sequence of subsets. They're no longer finite, but it has this infinite sequence of subsets, which is what it means to be C infinite. Okay, I also claim that it's H finite. And to argue this, I'm using the equivalence between H infinite and there's a countable sequence of finite sets. So there's something that needs to be explained. What does it mean for the permutation model to have a countable sequence of something? It means that the permutation model, that certain set is symmetric, and that set is the sequence. And the sequence is a bunch of pairs, 1A1, 2A2, and so on. It's just that this is a sequence that maps N to the nth element of your sequence. If this is going to be symmetric, it needs to have a finite support. So there needs to be an F so that every permutation fixing F pointwise needs to fix this setwise. But fixing this setwise means each of the first entries is fixed by default. They're pure sets. So what you really need is to be able to fix the elements of the sequence, but this time pointwise rather than setwise. So that's a criterion, and that's what allows me to do proofs. To show that some countable sequence is symmetric, it lives in the model, you need to prove that it's sort of like this thing that is slightly stronger than symmetric. You need to prove that there's a finite set such that fixing this pointwise fixes your set pointwise also, rather than setwise. And once I know that, I think it's easy to show now that A is H finite. suppose it was H infinite. Here's my set of atoms, by the way. So A0, A1, A2, AN. So suppose that there was this infinite sequence of finite sets. Such a sequence would have a finite support. This support is finite, and so it only has finitely many sets, whereas my sequence is supposed to be injective. So eventually some member of the sequence has some point sticking out of the support. And at that point, that's it. Because you need the support to imply that not only is the elements of the sequence fixed setwise, but also pointwise. But you can clearly prevent that by any permutation that fixes this and moves this somewhere outside of the corresponding set to which it belongs. So it's also H finite. Yeah, I'm about to finish because I'm running out of time. So let me just say what else is the set of atoms here. It's Rn infinite. I'm not going to go into details, but basically this model, when you look at each of the pieces of this countable partition, when you look at each of the ANs, within it, it's essentially like the first Frankel model. So the same argument that worked back then will work over here. You give me a coloring, either go to an AN that doesn't intersect the support, or if it intersects the support, just take the complement, but that infinite set will be monochromatic. And it is also E finite. And I guess I really need to finish now because of time, or in 3 minutes, and I want to say other things. So I'm not going to do the details of this one either, but it's very similar to this one over here. It's like if you go far enough, your supposedly surjective function has to just permute each of the ANs. That's more or less the idea. So when I have that information, C infinite, so this is above, H finite, so this one does like this, Rn infinite and E finite. Oh yeah, so that's what separates these. Okay, so this is third example. Okay, and so I'm just going to take a couple minutes for a few last few remarks. I don't need to look at any other model to complete my separation. Of course, I don't have time to go over the details, but the same third example, except that instead of the set of atoms, you consider a special set of sets of atoms, works to separate these two. And so when you look at that one, it goes like this: E infinite, H infinite, Rn infinite. So okay, so some other set in third example. And then as a last remark, or as a last thing I'd like to at least mention, I mentioned before that you have these implications, at least in the presence of something like the linearly ordered principle. So the other model that I would have talked about if there had been more time, basically now what you do is you take the set of atoms and you equip it with the structure of the random graph or the random n hypergraph for every n, and you run some of these arguments, and that you can use that to show that none of these arrows is reversible. But also I was checking whether that model satisfies the linearly ordered principle, and I'm not so convinced. So I'd like to state that as an interesting question if anyone wants to look at it. Can you still show that these are not reversible even with the presence of the linearly ordered principle? And yeah, I'm going to stop here.